Hi everyone, today we would like to discuss the hybrid energy systems and their role in shaping the future of sustainable energy. We are at the critical point, but you can slide. Okay. We are at a critical point in the transition to clean energy. Now, renewable resources such as solar, wind, or hydropower are gaining importance. However, the intermittent nature poses challenge to ensuring the continuous energy supply. This is where hybrid renewable energy systems offer a solution. Energy systems integrate different renewable sources with advanced storage technologies like batteries, supercapacitors, compressed air energy storage. Can be next. Air energy storage and pumped hydro storage to deliver efficient, reliable, and cost-effective energy. Research example highlight their efficiency. In China, hybrid energy systems produce energy at 22 cents per kilowatt hour, while in Morocco, combining solar wind or reduce cost to 0.0 $38 per kilowatt hours. These systems not only cut costs but also support rural electrifications and economic growth. Technological advances have further enhanced performance. Methods like genetic algorithm and participle swarm optimization. They improve energy efficiency and reduce fuel consumption and operating the cost. However, these are still gaps in understanding how energy source and storage methods interact. For instance, batteries provide fast energy response while power supports long-term large-scale storage. More research is needed to optimize these combinations. We can go with economically high hybrid research and renewable energy systems is not only environment friendly but also cost effective, saving fuels, lowering carbon emissions, and offering sustainable solutions, especially for off-grid areas. Looking ahead, hybrid systems will play a key role in achieving full renewable energy goals. With further research and investments, they can become scalable and widely adopted. We can go. In conclusions, hybrid renewable energy systems provide clean, reliable energy and pave the way for a sustainable future. Unlocking their full potential will require collaboration between engineer researchers and policymakers. Investing in their systems means securing energy for future generation. That's it. I leave the words Aya.
Hello, everyone. My name is Aygiri Matiyeva, and I'm going to continue the presentation with the elaboration on the methodology of this project. First of all, I would like to highlight the components which include the photovoltaic technologies, such as the monocrystalline silicone and the polycrystalline silicone. For the storage, the pumped hydro storage system is used, as well as the batteries. The main goals of this project include evaluating the renewable energy sources potential based on their availability in order to provide the best viability, the best cost analysis, the sustainability, and the energy efficiency. Throughout this project, the Homer Pro software is going to be used to analyze the hydropower systems. And the main focus of studies is based on the Ghazni village in Afghanistan. Next slide, please. So, as I mentioned earlier, the system will consist mainly of the solar energy and the hydropower energy. We can go to the next slide. First of all, the researchers, in order to supply the data for this project, started with the solar energy potential analysis at the selected site. And two main resources of the data that's been utilized for the studies are the Global Solar Atlas, which allowed us to estimate the tremendous solar energy potential of this region in Afghanistan, as well as the NASA's Weather Data Center, which provided us with information about the average solar irradiation of 0.2325 kilowatts per meter squared, with its fluctuations ranging from their minimum of at 0.13 kilowatts per meter squared, all the way up to its maximum of 1.06 kilowatts per meter squared. And as you guys can see on the second picture on the slide, there is a correlation between the solar radiation and the time, and as well as the temperature, which is very important for us to analyze, due to the fact that the energy production will really depend on the temperature of that region, and the temperature varies from negative 23.28 degrees Celsius in January all the way up to 31.23 degrees Celsius in July. Next slide, please. When it comes to the potential of the hydro energy at the selected site, there is an ideal condition for a hydropower to be installed, which is the fact of the presence of a river with 50 meters constant head and an average flow of 63.72 liters per second. Of course, there are some fluctuations with its range from 43 to 90 liters per second, and it's due to the fact that in winter there is the snow melt and precipitation, while in summer it's also getting reduced due to the precipitation. As you can see on the figure 4, there is a monthly stream flow rate in this region, and it does fluctuate. This is significant for us because we need to provide a reliable system that will work throughout the year. And sometimes the energy production will get lower, sometimes it will get higher throughout the year, depending on the flow. So this data is crucial for us. Next slide, please. Next, the authors analyzed the energy consumption analysis of this region, which consists of 80 households with a daily energy usage of 989.6 kilowatts per day. And the Homer Pro software has been utilized to analyze the hourly load profiles. As we can see on figure 5, there is the village hourly energy consumption profile, which highlights that the highest demand hours for energy are between 8 and 10 a.m. in the morning, and the lowest energy demand is between 3 and 6 a.m. as well, with a variability of 5% daily fluctuation. This information is significant as well because the energy has to supply to satisfy the customer's needs, which is the energy demand. And that's why we have to analyze the daily energy demand as well to ensure that the system will work correctly according to their needs. Next slide, please. And focusing on the Homer optimization tool, which main objective is to optimize a 100% renewable system with the photovoltaic and hydropower by minimizing the cost of energy as well as the net present cost and the environmental impact. This software is the main point of the project, and it does actually help a lot. The main methodology consists of 3 steps, which is the system configuration. Literally, it will help us define the components, like the community load, and enter the meteorological data. Then it's the input of the technical specifications and cost. And after that, it's followed by the optimization and comparison. So the cost of energy and the net present cost will be minimized. The configurations based on energy production and economics will get compared. I would also like to highlight the main benefit and advantage of utilizing the software. It's the load following policy. So it actually helps us to prioritize the renewable energy sources and prevent the waste of energy, due to the fact that when the excess energy is being produced, it can get stored in the power hydro system, storage system. And then when there is a low level of energy generation, the excess energy will be used to satisfy the demand of energy, which is actually good in terms of economy because it will reduce the cost of energy and reduce, of course, the environmental impact. And I think this is it. I would like to give a word to my classmate.
Thank you, Aya. Hello, everyone. I am Cem. I will present a comprehensive overview of a hybrid energy system that integrates hydropower, solar photovoltaics, pumped hydro storage, and battery storage. This system combines renewable energy sources and innovative storage technologies to create a sustainable and reliable energy supply. So let's dive into the details of how this system works and its key components. Overview of the hybrid energy system, our hybrid energy system integrates four main components: hydropower, solar PV technologies, pumped hydro storage, and battery storage. Each of these plays a unique role in meeting energy demands. While hydropower and pumped hydro storage produce AC electricity, solar PV systems generate DC electricity, which must be converted to AC for most end users. Converters act as bridges, ensuring efficient energy flow between these sources. This system is designed to balance energy supply and demand, particularly during peak usage times. Next slide, please. And yes. The key components of this system include energy converters like PV, sorry. So I will continue with photovoltaic model. Now let's talk about the photovoltaic or PV models. These are critical in harnessing solar energy, but their performance depends heavily on factors like temperature, solar radiation, and model type. In our study, we compared two technologies, monocrystalline silicon and polycrystalline silicon, like I mentioned. Monocrystalline silicon is more efficient with a temperature coefficient of minus 0.385% per degree Celsius and an 88% rating factor. However, it comes at a higher capital cost of $1,000 per kilowatt. Polycrystalline silicon, while less efficient with a temperature coefficient of minus 0.424% and 85% rating factor, has a lower cost of $900 per kilowatt. Both types of modules have a 25-year lifespan, making them long-term investments for solar power generation. Next slide, please. Moving on to the hydro model, the system incorporates a 100 kilowatts hydrokinetic turbine with a 50-meter head and average flow rate of 63.71 liters per second. This turbine is highly efficient with 80% of turbine efficiency and 90% of generator efficiency. The cost of this turbine includes a capital expense of $2,000 per kilowatt, with replacement costs slightly lower at $18,000 per kilowatt. Annual operation and maintenance costs are minimal at $20 per kilowatt. Like the PV models, the hydro turbine is built to last for 25 years, ensuring consistent performance over its lifespan. So I will continue with the pumped hydro storage and battery model. In terms of energy storage, the system uses pumped hydro storage and a lead acid battery. Pumped hydro storage involves a 1,000 cubic meter water reservoir paired with a 22 kilowatt generator operating at 90% efficiency. This system has a capital cost of $1,000 per kilowatts and annual maintenance cost of $100 per kilowatt, with an expected lifespan of 25 years. On the other hand, the lead acid battery provides 6.91 kilowatt hours of capacity at a nominal voltage of 6 volts. While its capital and replacement costs are higher, like $1,100 and $100 per unit, respectively. It has a shorter lifespan of 12 years. This comparison highlights the strengths and trade-off of each storage option. Next slide, please. So finally, let's look at the converters, which are essential for integrating solar power into the energy system. Converters transforms this electricity from solar panels into AC electricity for grid use. The system features converters with an efficiency of 95% and a lifespan of 15 years. The initial capital cost is $80 per kilowatt with less replacement cost at 90% of this amount. Annual operation and maintenance costs are estimated at 1% of the capital cost, making converters both efficient and cost-effective. So, in conclusion, this hybrid energy systems integrates diverse renewable energy sources with advanced storage technologies to create a sustainable and reliable energy supply. By combining hydropower, solar PV, PHS, and batteries, the system will equipped to meet energy demands efficiently. Each component from PV modules and hydro turbines to storage systems and converters has been designed for optimal performance and longevity. This system not only addresses current energy challenges, but also provides a model for sustainable energy solutions in the future. So that's all for me. Thank you.
Thank you, Cem.
I will leave the word to Verda.
Next slide, please. Now let's look at the economic analysis. Economic analysis is critical to demonstrate the feasibility and profitability of hybrid systems. While the upfront costs may seem high, the long-term benefits, both financial and environmental, far surpass these expenses. With increasing global focus on combating the climate crisis, funding from governments, NGOs, and private organizations supports the deployment of these systems. To evaluate the economic efficiency of hybrid systems, we use key metrics like COE, NPC, and CRF. These indicators allow us to estimate costs over the project's lifespan, including inflation and discount rates. For this study, an 8% discount rate was applied, which is within the rate recommended by the International Energy Agency. Next slide, please. We conducted 3 detailed case studies to explore various configurations of hybrid systems. This includes comparing 2 types of PV technologies, assessing the role of battery storage, and identifying the optimal solution for a fully renewable energy stub. In terms of energy efficiency, MSI system outperform in sunny conditions due to their crystalline structure, whereas PSI systems are more adaptable in cloudy or diffuse light. Economically, PSI is a more budget-friendly option, making it suitable for regions with limited funding. Next, please. This slide highlights the component capacities of MSI and PSI and the PV hydro PHS systems. The PSI system offers higher PV capacity, enhancing solar energy capture, while the MSI system exhausts an inverter capacity, ensuring energy stability. Both systems share consistent hydro and PHC capacities, underscoring their reliability. Next, please. This slide presents the performance metrics for MSI and PSI and the systems. While MSI demonstrates better reliability with lower unmet loads, the PSI system reduces excess energy and offers comparable energy production, highlighting its efficient energy management. Thank you. And now I'll leave the word for Betül.
Thank you. My name is Havva Betül, and I will be the summary of the all economic analysis. I will be doing all summary for economic analysis. This slide focuses on the economic analysis of MCI and MPC PV technologies. The PC system is more cost-effective with lower NPC and COA, making it suitable for budget-sensitive projects, while the MC system remains reliable with slightly higher operating cost. And this slide examines the component capacities of MC and PC technologies. The PC system lives in PV capacity for higher energy production, while the MC system features greater battery and inverter capacities, ensuring peak demand stability. This slide explores the energy performance of MC and PC technologies. The PC system excels in total energy production and capacity management, whereas the MC system offers better reliability with lower unmet loads. This slide compares the economic metric of MC and PV technologies. The PV systems lower NPC and CO make it more economical, while the MC system provides stability with slightly higher operational cost. And this study concludes that the PCE system offers the optimal balance of energy production, cost effectiveness, and reliability for the Zarsen community. With its lower NPC and COA, the PC system is ideal for budget-sensitive projects. While maintaining strong energy performance, future research should explore advanced renewable technologies and adapt these findings to other climatic conditions for broader application. Thanks for listening, and here's our reference.